Hello, good afternoon, and a very warm welcome to this latest edition of Steel via Technical Webinar Series presented by Steelmaking Events. Today we have roped in an expert to discuss on a novel breakthrough technology, which is HIsarna. HIsarna is a new and breakthrough process for the production of liquid hot metal from iron ore. It has a significantly reduced CO2 footprint compared to the blast furnace route, and the process is ideally suited for combination with carbon capture technology. This will result in a CO2 reduction of at least 80% over the whole production route. In the most recent campaign, the objective was to achieve process stability combined with a high level of equipment reliability and availability. In addition, the process is further developed in order to close the loop on zinc to increase circularity in the steel industry. This webinar presents the most recent pilot plant results in those areas. To introduce the expert we have with us today, graduated from Delft University of Technology with an MSc in Material Science. Mr. Boggelen joined Chorus Research and Development at their facilities in the UK in 2002, mainly working on converter steel making and ladle metallurgy. He got involved with the Haisana development in 2010, just before the first startup of the pilot plant. And Mr. Boggelen joined the Haisana project full-time in 2014. A very warm welcome, Mr. Boggelen, to Steelman's Technical Webinar Series.
Thank you very much for your kind introduction. I'll now try to share my screen. I think for most of you, I should say good afternoon. For those of you who are in Europe, good morning, and welcome to this presentation. I'll be talking about the latest results we've achieved in the HIsarna Pilot Plant, and hopefully give you an interesting insight in the development of a new technology with a great focus on meeting both the climate and the circularity targets for the steel industry, which in Europe are very big items, but I'm assuming that globally they are or will become soon very big topics. So what will I be talking about? I'll give a short introduction about Haisana itself. So how does it work and what are the key achievements we have achieved up to the last campaign? And then I'll tell a bit more about why Haisana will be a key enabler for both the climate and circularity targets, so for a sustainable global steel industry. And then a few remarks about the conclusions and some future developments. Well, first of all, for those of you who don't know yet, Haisana is a development that found its roots in the ULCOS project, which started in 2004 in Europe, and which was focused on developing technology to achieve 50% reduction of CO2 emissions in steelmaking in 2050. That 2050 is of course becoming a moving target, and I think everybody now aims for climate neutral steelmaking in 2050. So the 50% is more a 2030 target for a lot of countries and regions. In that ULCOS project, they analyzed about 200 different technologies, and 4 technologies were selected for further development, and Haisana was one of those. A key step in the development of the Haisana process was the collaboration with the HiSmelt company, a subsidiary of Rio Tinto at the time, because as I'll explain later, the Haisana basically consists of a reactor in 2 parts. And the top part of the reactor was already available within the Tata group, and the bottom part of the reactor, the knowledge and the know-how for that was supplied by this HiSmelt corporation. And in 2010, the pilot plant, as it stands now, just outside my window here, was built. And the key difference is that with conventional technology is that Haisana is a smelting reduction process, and we can achieve 20% reduction in CO2 emissions, but if you combine it with carbon capture, at least 80% is possible, and I think we can even achieve more than that. And I don't know if people can see my cursor, but in the diagram I've got a picture of the blast furnace, and the key processes that are required for the blast furnace is coking and agglomeration, so pellet making and sinter making, in order to charge the furnace. And the reason that you need that is that in a blast furnace you have the gas moving from bottom to top, whilst the solids move from top to bottom. The iron ore gets converted into liquid iron and slag and a load of gas, whilst these coke converts into gas, dissolves in the metal, and for the rest has an important role to play in carrying the weight of the burden. In Haisana, we don't have a solid burden, and because of that, we can inject iron ore in powder form and coal in powder form directly into the process, and we basically eliminate, therefore, all the raw materials preparation stages and the big plants that we need to do that nowadays. Then a brief explanation of how it works. So the Haisana process consists of two parts. The upper part is the cyclone, and the bottom part is called the smelting reduction vessel, or SRV. In the cyclone, we inject iron ore together with oxygen, and that is injected under an angle where the material swirls against the wall of the cyclone. In the cyclone, hot carbon monoxide rich gas from the bottom part of the process rises and is post-combusted by this oxygen, and the temperature increase that results in instantaneous melting of the iron ore. And it also means that the iron ore gets at least 10% pre-reduction, and depending on the gas composition, in particular the carbon monoxide content, it can be up to about 25% pre-reduction. And the liquid iron ore then drips into the slag layer here. In this slag layer we inject coal, powder coal, and this coal, this carbon, completes the final reduction stages. So it turns the liquid FeO into a liquid iron, dissolved with carbon dissolved in it. It returns the oxygen, or it turns the oxygen together with the coal into CO, and all the other components in the iron ore pretty much, that's all silicates, aluminates, they become part of the slag. To condition the slag, we do inject a little bit of lime with the coal. All other fluxes we inject together with the iron ore, so limestone and dolomitic dolomite we inject with the iron ore. Like I said, carbon monoxide gas escapes here and is then partly post-combusted in this section here, because the reaction, the reduction reaction, of course, means that there is a cost energy, which means that if we wouldn't add temperature, we would lose heat and the whole situation would solidify. The turbulence in this area then makes sure that the combustion, I want to take, so the turbulence here makes sure that the combustion heat is assimilated in the slag and the hot metal, and that's how we keep the hot metal warm. Temperature of the hot metal about 1400, 1450, slag about 20 to 30 degrees hotter than that. Gas temperature in the cyclone anywhere between 1600 and 2000 degrees, and the top gas that escapes is pretty much pure CO2, and the only difference at the moment is, the only reason why at the moment it's not completely, is because we inject the iron ore with compressed air, which has of course nitrogen in it, and we inject the coal with nitrogen for safety reasons. But we've already demonstrated that we can also inject the coal with carbon dioxide, so CO2, and there is no reason why we couldn't do the same with the iron ore. And if you do that, you have top gas that is pretty much pure CO2. Okay, then the things we have achieved so far. So in 2011, the plant was first started up, and that's when we did the first metal tap. And in 2012, we did the second campaign. That's where we demonstrated that we could actually operate the plant for longer periods of time, like up to a day and a half. Then in 2013 and 14, we managed to run runs of about 3 days continuously, and we demonstrated the energy efficiency that was originally calculated. We also supplied the first hot metal to the steel plant at that time. And in 2014, we did the first small-scale trials with zinc recovery and also with the addition of scrap. And then between 2015 and 17, we did a major plant expansion, where the biggest changes really were that the off-gas duct had a design flaw in it. So the whole off-gas duct had to be rebuilt to remove that design flaw. And until then, because we need our coal and our iron ore to be able to go through pneumatic injection systems, it needs to be dry and of a certain particle size. That was all done off-site, the screening and the drying, and to make sure that we could run longer without creating a logistical nightmare. We also built a coal grinding and drying facility and an iron ore drying facility, so we could create a continuous feed for much longer periods of time. So after the major revamp of the installation, we ran a project that was specifically targeting the CO2 reduction, where we had to demonstrate 35% CO2 reduction without carbon capture technology. And we achieved that by using, we attempted to achieve that by using 40% sustainable biomass in the form of a charcoal and 35% scrap. What we did was, for the biomass, we used a low ash, but also low density charcoal, and it was injected through one of the coal injection lances. And we selected a scrap that was very well defined, because the vessel is not so big, so a scrap feeding system is restricted in its size. So it had to flow quite easily through the scrap addition system. So from August 2017 up to July 2019, we have done a large number of plant trials and long runs, and the attempt was always to run as long as possible. And what you can see here in this diagram is that initially we've not been running the plant for nearly 3 years. That initially we really struggled to go beyond the number of days we made in the past, and here we even went through a period where we really struggled, and most of the issues here were maintenance related, so bits of equipment just breaking down and stopping you in your tracks. Recently then, later, we managed to create a better, more stable equipment, but also to improve the process stability a little bit. And we managed to run for like nearly a week, 10 days, that sort of order. And then sort of early 2019, we managed to realize managed to grasp some of the key issues that resulted in the process instabilities that we have been suffering from. And that immediately resulted in much longer runs of 19 days, where actually the process stability has not been an issue at all. And we start for these long runs running into equipment stability issues again. So the longest runs we've done, March and July 2019, 19 days each. The highest production in a single run, 2,000 tons of hot metal, so just over 100 tons of hot metal a day. This graph sort of shows the blue line is the continuous increase in hot metal weight, in hot metal tapped. The pink line shows the slag taps, so we weigh everything we put in, and everything that comes out is weighed, so we know exactly where everything went, hopefully. So we also weigh all the dust and stuff like that. The only thing we can't weigh is the gas production. The other thing we have achieved is we managed to recycle 100 tons of BOF or LD slag as a fluxing agent to replace the limestone and dolomite we're using. That worked really well, actually. So for us, a key development that would have to happen for relatively soon, in my opinion, is that we have a process here on the site that could granulate LD slag efficiently in the right particle size, because that would save us buying limestone and dolomite as a fluxing agent. And it also is a much higher value application of LD slag than if you would follow the route where it goes now, where in our site it largely goes for road stone and hard standing. And the other thing we demonstrated is that we used CO2 as a carrier gas, as I'd already mentioned. So, of course, we have achieved these things on the pilot plant scale, but to know what will happen if you actually make a larger scale facility, you cannot just multiply it by whatever scale you go to. There is other things to take into account. And the good thing is that as part of this ULCOS project, to compare all these technologies, a tool was developed called the CO2 tool, that allowed all these different technologies they analyzed, allowed comparison against each other for them, where they basically developed a standardized steelmaking site that makes 4 million tons of hot rolled coil, and you could change the layout of that site. But sort of the output was always the same. And then you can easily calculate the CO2 per ton of steel coming out of the site. And using that model and the pilot plant results, we then could demonstrate that if you use scrap or biomass, you already reduce the CO2 footprint significantly compared to the standard blast furnace, and also to the original Haisana calculation that was done with the model. And if you combine the biomass and the scrap in the best combination that we'd achieved, you go to about 40% reduction in CO2 emissions. If you take the two best points we achieved on biomass and scrap, you even halve the CO2 reduction across the route. And that is without carbon capture. That is purely by emitting less CO2, but assuming that the biomass you use is a truly sustainable biomass. If you then go a bit further and combine Haisana with carbon capture technology, then you can see that you could achieve negative emissions if you have biomass and carbon capture. So we are really looking at combining the Haisana pilot plant with actual carbon capture technology to prove on a smaller scale that it's possible, and also already trying to identify any snags in the scale up that we might encounter. Another thing that gets a lot of attention is circularity, and particularly in Europe, it's a very big topic, because Europe is realizing, and I think the whole Corona crisis has even emphasized that more, that for its raw materials, Europe is very dependent on the rest of the world. And there is a large program within Europe to actually recycle and reuse as much of the materials as possible to minimize the need for raw materials needing to come in externally. And what we can do is use scrap in the Haisana process in relatively large amounts. And actually, the other thing that we have as a benefit is that we can actually use large amounts of zinc coated scrap in the process. And I'll come to that a little bit later. First, about the carbon capture. Together with the Dutch Research Institute, TNO, we are working on different routes to sort of find outlets for the CO2. Holland is very conveniently located on the North Sea shore, where there is a few empty gas fields already, and there is also the opportunity for enhanced oil recovery. But we do realize this is only a temporary solution. And for a CO2 a longer term solution for CO2, if there is still a carbon capture and CO2 production, is that you need to find applications for the CO2. One would be supplying food grade CO2 for growing crops, or use in food applications. But there is also lots of projects in the development of chemicals, or you can use CO2 to set concrete and stuff like that. But outlets for CO2 would be an important future step, I think. Now, then the good thing is that if you build a Haisana plant that has pretty much pure CO2 coming out of its out of the top of the process, going through its gas cleaning and scrubbing system, and then you feed that complete feed into a CO2 liquefaction plant, you've basically built a plant that has no stack. And if it has no stack, it's not just that you have low CO2 emission, no CO2 emission, you also eliminate the emissions of nitrous oxide, sulfurous oxide, and fine particulates from the stack. And that is not so much a climate issue, of course, but it's very much a local and regional environmental issue that you can tackle simultaneously with tackling the CO2 emissions. And on the zinc recovery, this is also part of a European project under the EIT raw materials banner, and together with Nearstar, who is one of the suppliers of zinc to the steel industry. And what we do is in integrated steelmaking, we try to avoid the use of zinc-coated scrap, because the zinc is released as dust, vapor and dust in the steelmaking process, and most plants recycle that dust via the blast furnace, and zinc in the blast furnace can be a real problem. So for that reason, they tend to avoid the zinc-coated material, or put it through a de-zinking stage first. The problem there is, of course, that as an industry, we actually make a very large amount of zinc-coated material for cars, for construction, you name it, and there is a zinc-coated application for it almost. And as a result of that, there is actually large amounts of galvanized scrap leaving Europe and going to countries like Turkey and other places where it's used in electric arc furnaces for lower grade applications than the very well-defined high grade applications that the steel was originally made for. So it's not really recycling, it's more a form of downcycling. And EAF dust can contain up to 35%, but a lot of places it's around 20% zinc, which is then upgraded via intermediate processes, including the weld kiln, to be used as a raw material for zinc production. If it's much lower than the 20% zinc, which also happens, it's often just landfilled, and that zinc is lost. But by recycling in Haisana, what you can do is, because of the temperatures in the process are so high, all the zinc evaporates, and we can concentrate the zinc in the final bag filter with the fine dust. And the aim is to make a zinc concentrate that has more than 50% zinc in it, which makes it suitable for direct use in zinc refining. So the intermediate stages can be skipped, all the pre-processing stages. And this is getting close to a prime ore for zinc. And that way we close the loop two ways. So A, you can recycle the very well-defined zinc-coated material back in integrated steel making, and at the same time you can recycle the zinc dust back to the zinc smelting industry, who can supply us with metallic zinc to make new zinc-coated steel. Well, then few of the key economic benefits. Haisana has a relatively low OPEX compared to the standard route, so there's no need to blend or agglomerate the ores or to coke the coal. And because of that, you don't need any intermediate stocks between all these processes, so you have a lot less working capital, a lot less stock. plus all these processes also have a cost related to them. Haisana is actually quite suitable for lower grade raw materials. We don't need any coking coals, so that will save us quite a bit of money, I guess. And also in the type of ores we use, we can be a lot more flexible on the blast furnace. And one of the key advantages for us is that we separately tap the slag and the metal. So if we have a grade of ore that produces a bit more slag, it's not necessarily hampering the process as such. We can easily use this the sort of waste oxides and BOF slag, which we have already demonstrated. We've demonstrated the high energy efficiency. And because we produce a low silicon and low phosphorus hot metal, actually the cost in the BOF shop, in the LD shop, will be lower as well, because you do not need as much flux. That means you have a much lower slag volume. That means you have a much higher process yield. So that gives a lot of benefits. And then for a greenfield development, well, you can imagine if you don't need to build a coke plant and a sinter plant, the total money spent is a lot less, of course. So in conclusion, it's a breakthrough process that offers significant environmental and economic benefits, and it will be an enabler for a sustainable global steel industry. And it can achieve very large CO2 reductions. We've proven 50% without carbon capture. We think more than 95% is possible with CO2 capture if we get it right. It can be emission-free, environmentally neutral, and that means that not just the CO2, but also nitrous oxide, sulfur oxide, and dust emissions are much reduced. And it can contribute in large extent to a circular economy. We're focusing on zinc, but we also see opportunity for recovering other materials from either dust or slag streams from the process. And therefore it lowers, and on top of that, it offers a low-cost steelmaking solution. Just all the acknowledgements at the end. So we don't do it by ourselves. It's developed together with ArcelorMittal, ThyssenKrupp, voestalpine, and Paul Wirth. And we have received funding from several bodies within Europe and the Netherlands to achieve what we've achieved so far. And thank you for your attention.
Thank you so much, Mr. Boggelen. So the initial question that we would like to ask you, sir, is now that I believe that the fifth phase of the campaign for Haisana is already over. And now we are going into the next phase, which is the sixth phase, and which is supposed to be the industrial phase of the technology. So what is kind of capital expenditure that is required for setting up, designing the industrial site, the industrial plant, industrial facility?
Well, I can't give any exact figures, of course, for capital expenditure, but in the end, it's still in the same order of magnitude as building just a blast furnace. Not forgetting all the things you need around a blast furnace, because it will, in size and scale, it will not be far off that of a blast furnace. So you need similar facilities in cooling waters, in oxygen supply and nitrogen supplies. You need the same amount of space, and the total space of the volume that the installation takes up is probably also very similar. So I would imagine sort of similar order of that, but I cannot be more specific than that.
So the pilot phase, the capacity was around 65,000 tons of molten pig iron.
Yeah.
So what is the kind of capacity do you estimate will be there in the industrial facility?
Well, we believe that the first industrial scale facility would probably operate sort of near the 500,000 ton mark. But with the same size vessel, we probably could be able to make more than 1 million ton as well, depending on the feedstock and also ramping up of the installation. We are convinced that there is a lot of room to gain a lot without necessarily making the plant any bigger than our initial industrial design.
Right, sir. And so, what do you think are the main technological challenges that are involved at this industrial stage of the technology of the iron making technology?
Okay, yeah. The key, the biggest, initially, the biggest problem was really the fact that in a pilot plant, you build things for experimental design and you're not necessarily design it for robustness. So that was where we were. But we've replaced most of the systems that were a bit fragile with more robust systems, and that has sort of proven itself. The key technological challenge that we're facing at the moment is the refractory wear, because we have a very turbulent process with a very aggressive slag that has iron oxide in it. The refractory wear in that section is high, but we are working on a solution that hopefully gives us much better refractory performance. And the other things in upscaling that we can only model and not really prove on the pilot plant is one, is how far can you scale a cyclone? Do you make the site? You cannot go infinitely wide, of course. There is a point where you cannot go any wider without losing too much. And also a very key aspect of the business case for Haisana is the ability for heat recovery. The Haisana process produces CO2 as a process gas, so there is no calorific value in the gas. It's only sensible heat. So we need to have a boiler system that recovers that heat, but can cope with a gas that has a significant percentage of dust in it. So that is a challenge that those two are, I think, the key challenges to solve.
Yes, sir. Yes, sir. Sir, could you kindly, going back to the converter, the cyclone, the cyclone technology that you were talking about, sir. So the cyclone technology was already available, I believe, with Boggelen for a long time, which was subsequently, adopted by Chorus and then Tata Steel Europe.
Yeah, so the cyclone, the idea of the cyclone is actually very old. The cyclone furnace ID started, I think, in the late 1960s or something like that. But they were only tested in anger for real in the 1990s here on the site in Amuiden. And the research then was driven by coke pricing. So they were looking for a coke-free iron making process. But then at that time, coke prices were very low and very stable. So the business case to continue that project wasn't there. So the project was paused, and only in the Ulcos project, in the Ulcos project, the cyclone appeared again. And actually, the cyclone that we have in our pilot plant now is exactly the same cyclone that was tested in the 1990s on the site here in Amuiden.
Right, sir. So this Haisana technology is basically a marriage of the cyclone technology as well as high smelt, which was developed by Rio Tinto.
Yeah, I mean, there is a little bit more to it, but crudely, you can say we've basically bolted a cyclone on top of a high smelt vessel. And the big difference with high smelt is that high smelt still uses a hot blast lance that blows in straight from the top, and the Haisana process is completely oxygen based.
So if you could give us a rough estimate of the kind of oxygen that is used per ton of hot metal in Haisana.
I'd have to look that up. I'm not 100% sure. I can shout a number here, but I'd rather check that first.
Okay, sir. And the iron ore, what should be the grade of the iron ore that we can use? Because you've already mentioned that we can use fines, we can use powders, iron ore powders, iron
Yeah.
powders. And coal also we use in a powdery form. So what is the kind of grade of iron ore that is ideal for Haisana?
So for us, our normal testing, we actually use high-grade ores that are similar ores that go into our blast furnace, simply because it's easily available and it gives us a high level of stability. But we have already demonstrated that we can use iron ores with only 30% iron. It still works, but we make a lot of slag then, of course. So there is an economic trade-off between the iron ore price and the process yield at one point where it makes no sense to do it anymore. But we have demonstrated that the really low grades can still be processed in the equipment. Whether it's economically sensible to do that is a different matter.
So, I mean, like from an economic and commercial perspective, what is the kind of grade that producers can look at using? From 60 to 62%, 64%? Iron
It's
content.
at the moment the grade we use would be in the order, it would be mid 60s somewhere. Yeah. So the 63, I think. Well, I'm not 100% sure the detail, but it's a standard ore that goes in our blast furnace as well.
And so the coal that is used, what is the volume of coal that is used per ton of molten pig iron?
So at the moment in the pilot plant, we use about 800 kilograms per ton. However, we think if the plant is scaled up, we can reduce that significantly. Of course, with the small plant, everything that is above the slag level is water-cooled copper panels. And we have a relatively poor surface to volume ratio on the pilot plant. So around 25% of all the energy we put into the system disappears via the cooling waters. If we scale the plant up significantly, that 25% will drop to like 5% or less, and that will have a very big impact on the coal consumption. So we are convinced it can be significantly less than normal blast furnace operation.
Plus also coking operations are dispensed with, so which is basically an eco-friendly process.
Yeah, so for the blast furnace, you need to add up all the carbon used there, so also the carbon used to make your sinter and all that sort of stuff, to make a fair comparison.
Right. And so the kind of the grade of coal that producers should look at, coal of what kind of a calorific value? If you could just give us a.
Not from the top of my head, don't know the calorific value, but we've used coals with a very wide range of volatile content, and we've basically tried anything from less than 10% volatiles to nearly 40% volatiles. It all works, but if you get to 40% volatiles, you make so much gas that the plant is difficult, or if not nearly impossible to operate. But we normally run anywhere between 10 and 20% volatile content, for example.
Right, sir. So to return to the European Union program of this European Union program of cutting down emissions from steel making process, there are different kinds of DRI technologies that are now being I mean, experts are talking about many different kinds of DRI technology now, which are alternative to the integrated route. Like we know about Finex, for example. We know about, for example, Corex. So, what do you think will be the distinctive or the unique feature of Haisana that could, really promote its adaptability?
Yeah. So if I look at smelting reduction processes, I think Haisana has a big benefit over, for example, Finex or HiSmelt, in that the pre-reduction stage is included in the liquid process, in the liquid stage of the reactor, which makes it extremely efficient. Basically, what normal processes do, the blast furnace included, is that you do a lot of the pre-reduction in the solid phase, which is slow and inefficient, and then melt everything and then do the final reduction. In our case, or even do a large amount of the reduction in the solid phase with DRI. It's pretty much all in the solid phase. In Haisana, basically you melt everything first and then you do the chemistry, and that makes the chemistry really fast. So compared to, for example, a blast furnace as well, the process is very dynamic. It's much more like an LD converter from its dynamics perspective than a blast furnace. Things change really quick if you don't get it right. When it comes to smelting reduction, I think the key there is that you have the pre-reduction included in single reactor. And for example, with Finex and also with HiSmelt, there is always sort of this ore preheating and pre-reduction with fluidized beds and coke beds and that sort of stuff. We don't have any of that. So all our raw materials are injected into the process at room temperature. So that makes it very easy. Compared to DRI type processes, well, the biggest advantage of doing a process like Haisana or any other smelting reduction or blast furnace process is that at the smelting stage, you separate the metal and the gangue or the slag component, where if you make a DRI, you do not do that separation until you do the electric arc melting stage. And then certainly if you're trying to make steel directly out of that, you need to handle that large slag volume. With respect to the DRI, if you've got cheap natural gas or cheap hydrogen available in large quantities, there is probably economically totally sensible to go that route. But it hinges on the availability of large amounts of cheap gas. And well, even though in Holland we have large gas fields, we don't have cheap gas, for example.
Exactly, sir. Exactly, sir. So just to get back on the the European Union's objective of cutting down on emissions, if they've given a timeline till 2030, what do you believe could be the total amount of emissions reduction that is possible, considering the industry today and the technological developments that are going to happen?
Yeah, I think the 50% should be possible, but it requires large amounts of investment. I think the technologies that we need to do that are there or nearly there. And Haisana is one of these technologies, but I'm also looking at the hybrid development in Sweden, for example, or the other DRI and electric arc processes. A lot of the technology is there, or is about to be commercialized. And but if you look at the investments needed throughout Europe to achieve that, it will be tens of billions, if not hundreds of billions of euros that need to be invested across the continent. And Europe has a large number of relatively old steelmaking sites where it's not easy to start anew. You have to sort of gradually change it over, and that makes it very difficult to make the right decision at the right time, I think, because you need to have the money and you need to sort of get the timing right, and you need to still make steel at a price that is in line with pretty much everybody else. So I think technically it's not a problem. I think the problem is largely economic.
So the problem is with funding, mainly. And sir, actually, many major integrated steel makers like ArcelorMittal and all, they have already shared the kind of investment that is required to phase out the old ways of steel making and introduce new ones. What do you think will be the government's, the European Union's role in this regard, as far as introducing carbon credits are concerned, or developing the infrastructure for carbon storage and utilization?
Yeah, so I think that it's important that if we want Europe to act as one in this, and that these technologies come off the ground, that the climate needs to be created for that to be done. And that doesn't always have to be money from the European government or the national governments, but making sure the infrastructure is there. Yeah, and if we want to do carbon capture, we're going to need a big CO2 infrastructure. If we want to use hydrogen, we're going to have an infrastructure to take the hydrogen around the country. And if we want to use all green electricity, we need to build the wind turbines that are required to make that. So there is, I think, a lot on the infrastructure side and on the creating the right landscape side, policy driven, that national and regional governments and the European government for Europe. But I'm assuming that China and India and South Korea will face the same problem now or in the near future. So
Yes, sir. Yes, sir. Sir, actually, pre-combustion and post-combustion carbon capture and utilization. So post-combustion carbon capture utilization that for the iron and steel industry, sir, is it a very costly process? What would be the cost like per ton of steel produced?
I don't know if I can't give the exact number, but it will be in the order of tens of euros per ton, and it all depends on the CO2 level that you achieve in the gas. The higher it is, the less gas cleaning and stripping you have to do before it's suitable for application in a carbon capture and storage or carbon capture and utilization scenario. Uh, um, uh, so looking at the cost of CO2 rights in Europe with the CO2 trading scheme, if the prices keep rising, then carbon capture would probably be economically feasible compared to the rights you have to buy otherwise.
Right, sir. At this point, I would like to request our audience, members of the audience, participants also to send in their questions along with their names and the name of their companies, so that we can, put those questions forward to Mr. Boggelen. Yes, sir. To continue with the carbon capture and storage infrastructure that we were talking about. So, do you believe that carbon capture and utilization or storage could be made economically feasible by diversifying the uses of stored carbon? Its uses in many different fields.
Well, I'm convinced that we're going to need that because even though I hope that we get to a point where we can use large volumes of hydrogen in the steel industry, I think a steel industry without carbon is unthinkable, if not impossible. And because in the end, steel is an alloy of iron and carbon, of course. And that probably means we always need some form of CO2 capture in a lot of places to really genuinely meet the zero emission target. And not everywhere in the world is as suitably located as the Netherlands, where you have empty gas fields nearby where you could store it. And also that storage is in the end only limited. So we're going to have to come up with ways to actually use that carbon dioxide as a raw material. And there is a lot of work going on in finding applications for it. Of course, the food grade and using it to grow crops is one of them, and algae and whatever you can think of. But I know there is quite a bit of work on using it as an enhancer in concrete, setting of concrete. And there is quite a lot of research in using CO2 together with hydrogen and electricity to make chemicals. And personally, although it's only a very small scale at the moment, I'm very interested in following some of the research on actually turning CO2 back into carbon and oxygen and closing the loop on the carbon and the oxygen. If I use all this excess green electricity to make hydrogen, why not use it to make carbon out of CO2 again? Carbon for the industry, carbon is a much more convenient reduction agent and energy carrier than hydrogen because it's solid, it's very compact, it's easy to transport, it's very easy to store, where hydrogen is none of that. It escapes out of everything. It's large, it always takes up a large volume. It's very difficult to have large buffers of hydrogen in case there is a day of no wind or no sun. So I think carbon is a much more suitable energy carrier. However, the technology to make hydrogen is quite mature. The technology to make carbon out of CO2 is at lab scale at the moment.
So talking about hydrogen, do you really believe it has the potential to replace carbon in say till 2050 in Europe? I'm not talking about the world, of course. in Europe? Does it have the potential?
My biggest concern is that the amount of hydrogen you would need is just simply not there. Well, the hydrogen is there, but it's in the form of water. So the electricity you need to make that hydrogen is going to be the bottleneck. Because yes, we can turn the whole industry into a hydrogen-based industry with the electricity, but we also are all expected to drive electric cars, and we're all are expected to use electricity to cook on instead of gas, and or can think of about 20 other things that we need to do with that electricity. And the problem is simply is that our electricity use is going to keep increasing, and we're not necessarily generating or building the green energy generation capacity fast enough.
Right, sir. So now coming back to Haisana, we were talking about these integrated steel plants and how the old equipments and facilities will be phased out. So can Haisana be applied to a brownfield project, or ideally should be a greenfield one? What do you think?
Well, I think in a greenfield situation, the choice is a lot easier, I think. And the design and the construction, you can see the investment needed is a big advantage, unless you build electric arc furnaces. But if you want, then it might be a bit close. But if you compare a blast furnace to a Haisana, it would be easier to build a Haisana, a lot easier. In a brownfield, and that's where we're actually developing ourselves, because Tata, so both for India and for Europe, we see the Haisana as being part of the existing steelmaking infrastructure, replacing some of the old equipment eventually. And that means it has to be integrated in brownfield situations where you have these gradual changes from one technology to the next. And that also is a challenge in itself, because we cannot switch the old one off until we know the new one actually works, and that is a big challenge, and also it involves quite a bit of risk, to be honest.
Right, sir. Right, sir. So I was just, I was reading somewhere. I remember that Tata Steel India is willing to set up a Haisana facility at its Jamshedpur plant as well in India. And but the main technological the developments or the testings or whatever will happen in Holland. So
Yeah.
so is that right, sir? Is Tata Steel building a Haisana facility in Jamshedpur?
Well, they haven't started building yet, but they are in the design stages of designing a Haisana that will be built at the site, at one of the sites in India, most likely Jamshedpur. That's correct. And all the testing for that. So the basic principles of the process we've basically proven. But for example, the raw materials mix in India in Jamshedpur is quite significantly different from what we have here. So in that respect, there is still quite a bit of research to be done on the pilot scale plant to help define the operational windows for the industrial scale plant.
Could you just give us a rough idea as to what would be the capacity like if a Haisana facility is ultimately built in Jamshedpur?
So, like I said earlier, it will be around 500,000 ton capacity is the initial sort of stage.
Right, sir. And so just I know we wanted a glimpse from you about coal and where is Europe moving as regards coal is concerned. Now, this highly polluting technology, highly polluting commodity, and now coal is being slowly and slowly phased out. But then, how will the European integrated steel industry survive without it?
Yeah, so there is a big drive in Europe to phase out coal. The focus at the moment is largely on power stations. So coal-fired power stations are being closed and being replaced by either gas-fired or nuclear in some countries, depending on but also a lot of solar and wind power. I think once the power stations are sort of gone through the largest change, the steel industry will have to do the same. And it seems to be going several ways. Some regions or countries or companies seem to be completely focusing on an electric route, so going electric arc furnace or combining that with DRI. And I think the different news articles that have been coming out in the past week alone sort of show that different steel companies in different countries have quite different approaches to this problem, but all of them, because in the end, the energy has to come from somewhere, I guess. So they all, if they move away from coal, it goes natural gas, hydrogen, electricity.
Yes. So there is no other alternative right now.
Yeah.
Yes, sir. Sir, just little curious to know that you were saying that some 50% of the burden could be the charge burden for converter steel making in the
Yeah.
Haisana. So, sir, the scrap can be lifted to 50% of the total burden.
Yeah, we've done so. We've run at 53% scrap input, and the yes, you use coal to melt the scrap, but it's extremely efficient. You need very low amounts of coal to melt the scrap, and the scrap is very you get a very high yield out of it. So it's a surprisingly, we thought it might be more difficult than that, but because the process inside is so turbulent and the mixing is so good, as long as you give a continuous feed of scrap that gives the opportunity for good mixing, it appears to be working really well to have a high scrap load.
Scrap load.
Yeah.
Scrap load. So, so it increases the efficiency of the process.
Yeah, significantly. So, and the outcome is still a hot metal. So you turn the scrap into a hot metal, which helps if there is any. So you can also use scrap that is slightly less pure, because you can use the refining stages in the steel plant. However, things like copper, tin, molybdenum, they will always remain a problem, of course. So we still need to be aware of those. But things like zinc, or if you get a high or a low phosphorus type of scrap, it doesn't really matter whether you're making a low, the steel coming out of the iron coming out of the Haisana is always low phosphorus and no silicon.
Right, sir. Right, sir. So now just shifting the focus a little bit from Europe, maybe just for 1-2 seconds if possible. So Heisman technology is being developed, as you know, in China after the botched project in Australia. It finally went to China, and they are now developing the technology. Although they're just developing it on still on a pilot scale, and no industrial facility has come up. In India also, you must be aware the DRI facilities are mainly coal-based, because natural gas is not very widely available in India, or even if it's available, it's very costly. So, how do you foresee the future of Haisana in emerging markets like India, like Southeast Asia?
I think those markets are actually extremely suitable for Haisana, because they offer such great flexibility. So what we've demonstrated here is that it can be 100% coal-based, and that it can be very flexible about the types of coal you use. With the coal you use, the biggest challenge is probably the sulfur level in the coal, because Haisana is not so good at desulfurizing as a blast furnace is. And the same applies probably to the iron ore, though some of the big differences between iron ore from India and Europe we haven't really investigated yet, but the grade shouldn't be a problem. It's more about the gangue composition that we need to investigate much further. I think the way we are looking at the process now is that, yes, we have developed Haisana as a coal-based process, but we can see clear opportunities to actually reduce the coal need for it, and also introduce natural gas and or hydrogen to replace part of that coal we use, reducing the carbon need for the process and introducing a hydrogen component to it. And if we manage to do that, I think you have an extremely flexible process that would be suited for many different types of economic conditions, and can be very responsive to any changes in raw material markets and energy markets.
Right, sir. So, but but there are, of course, there are quality concerns, like as we mentioned, about the desulfurization of hot metal in the blast furnace route, and compared to that, the Haisana route here. Also, cutting down our dependence on coal by using hydrogen. So, how will that affect the quality of the product?
Well, the Haisana process as such supplies a hot metal that is not dissimilar to a blast furnace hot metal. It's got the main components in there, but it's slightly lower in carbon, about 4%. It's got virtually no silicon. It is low in phosphorus, and depending on the coal you use, you get a average to maybe a little bit high sulfur level. Now, the sulfur removal as such is technically not a big problem because steel desulfurization and also hot metal desulfurization are very common processes. So we believe that that is a problem that can be solved. And then what we do see is that because of the low silicon and the low phosphorus, it actually makes the steelmaking routes cheaper and more friendly, environmentally friendly, because of the lower slag volumes that you need. And because of the low phosphorus, we believe it opens the possibility for a wider product range on the steel side. So because of the low phosphorus. Or if the phosphorus in the steel product is not so much the problem, opens a route for lower grade raw materials that are, for example, higher in phosphorus to start with, because you get such good phosphorus refining in Haisana.
Right, sir. Right. So with that, we start, taking questions from the audience, and I can see there are quite a few already lined up here. Mr. Cabello from Afroval Metallics in South Africa asks, would you kindly expand on the use of CO2 for growing crops as per slide 10 that you showed, sir? Is anyone around the world who is producing food grain from carbon dioxide?
I don't know any specific names, but I do know that in Europe last summer, not this summer, last summer, there was a shortage of food grade CO2 because several plants that produced the CO2 as a byproduct were in maintenance stops, and companies like Coca-Cola were struggling to get enough CO2 for their cola. And I know that in parts of the Netherlands, there is actually a CO2 network that supplies CO2 to the greenhouses to enhance the tomato growth and that sort of stuff, So it is already done. Which companies exactly and how big their market share is and that sort of things, I don't know.
So Mr. Swapnil Kaushik from India, he hasn't mentioned his company name, is asking, is the target worldwide is to decrease or avoid CO2 emissions? How the Haisana fits in, because it is still a coal-based iron making process.
Yeah, so the key thing here is that, yes, it's coal-based, but I think if we get it right, it's much more efficient. So you reduce significantly. But I think if you want zero CO2 emissions, Haisana has to be combined with some sort of carbon capture technology. And then there I am really hoping that besides the steel industry, other industries look at CO2 as a source, as a raw material to make new chemicals, to use it for crop growing, to, I don't know, you can probably think of things you can do where you need carbon and oxygen together, or that the technology to convert CO2 back into carbon gets to a scale where it's economically feasible to do it at an industrial level.
Yes.
And at the same time, I think for us, there will be a big driver to replace as much of the carbon as we can with natural gas and hydrogen. How far we can push that, I don't know, but we definitely will be trying that.
So Mr. Satyajit Jain from India also has a very interesting question. Once you ramp up Haisana over time, what do you do with the current blast furnace capacity?
Yeah, so well, here in Europe, it would mean that if we start running the blast furnace of Haisana at its design capacity, we would have to shut down the blast furnace. And that is in the end also the objective, is to replace the blast furnace by Haisana combined with maybe DRI or maybe to get the same capacity. It depends a bit on the conditions at that time. If you look at probably on the Tata Steel Europe website somewhere, there is a strategy for Tata Steel Europe to be carbon neutral in 2050. And for the Amouden side, you can see that there is a genuine plan to shut down at least one of the blast furnaces in that whole cycle. And that means that's what you do with the current blast furnace capacity. If you have a site where you can use the extra hot metal without compromising your steel making, I think the initial step would be to just run it on top of what you already have and keep the blast furnace capacity going. That doesn't reduce the CO2 output of your site, of course, but in a demonstration plant situation, I think proving the technology probably takes preference over driving down the CO2 immediately and risking the loss of production altogether. It's a difficult choice to make, because of course we should all be working on reducing the CO2 emissions as fast as we can, but there is also still a big demand for steel.
Naturally, sir. So, as you just mentioned that yes, greenfield applications are, they are well desirable, but there could be some phasing out of old capacity as well. With the slow growth and development of the technology, there could be some phasing out of the old capacity as well.
Yeah.
Yeah. So going now to the next question, what modifications are required in current steel making to convert in order to implement Haisana process, and what is the cost benefit? This is the question being put forward by Mr. Ashwini Kumar from India.
Yeah, so the actual cost benefit is again a number I cannot disclose. It will be cheaper and significantly cheaper. The modifications that you need in the whole route is not that dramatic. So yes, on the iron making side, you would be replacing existing sinter making, coke making capacity by a Haisana, so you close facilities. But the hot metal that comes out of a Haisana, it should be possible to process that in a BOF converter, an LD converter, in a similar way as hot metal, with the difference that you have no silicon and low phosphorus, so you cannot add as much scrap in your converter. But it will look very similar to the second stage in the two converter or two blow practice that is used in some steel plants in Japan, China, and Korea, where they try to make a short blow for desiliconization and dephosphorylation, then remove the slag or tap the hot metal again into a next converter, and then just decarburize. So you could run a Haisana hot metal in a converter as just decarburizing.
So a very general question from Mr. Shubhrato Mukhopadhyay from India. India being the second largest producer of steel in the globe, what do you think India can contribute in producing steel in the near future?
Well, I think India's got a lot to offer, to be honest, and but at the same time, I think India also needs what it produces almost all by itself, because it's still growing very fast. So I think, however, that creates an ideal landscape to develop new technologies that improve efficiency and that drive the cost of steelmaking down. Because there is such and we've seen it with China as well, but it's sort of stopping a bit there. It's the fact that you are building new facilities and upgrading existing facilities at a much higher rate than, for example, Europe. it would be a good proving ground for new technologies.
So Mr. Zak Abdullah also from India is asking that using powdered iron ore and coal, what could be the effects of using powdered iron ore and coal instead of coke in terms of impurities in the final product? And also in terms of refractories, what development methods will you use to improve the wear resistance in the Haisana process?
Okay, well, the impurities in the final product is actually not a problem because the coal and also in the iron ore, everything it becomes liquid or gas in the reactor. So the separation is very good. So the only impurity that we get in the hot metal that we really try to keep as low as possible is the sulfur. The rest is actually no different than a blast furnace or better. When it comes to the refractories, we are working on refractory that is actively cooled to protect it. And hopefully in the next sort of 6 months to a year, we can present a beautiful paper on how that works.
Sir, could you just, a question from my side, could you just tell us when is the next campaign starting from? And what could be the duration of the campaign?
So the next campaign is started as soon as possible. The problem here at the moment is that in the Netherlands there is a legal problem nationwide with the emissions of nitrous oxides and the deposition of that in protected nature areas, and that makes it so there is that results in some issues around permitting, and this is a problem throughout the Netherlands. Actually, it's really a nationwide issue, and we are trying to resolve that. And as soon as that is resolved, we can hopefully start the campaign. But we are pretty much ready to go. And in that campaign, there will be the focus will be on further improving the equipment reliability and stability, but also starting to prove the raw materials flexibility to a much greater extent than we've done so far.
So by raw material flexibility, you mean the kind of grades that they use? Different
grades, but also particular the different gangue content. So some iron ores are high in silica, others are high in alumina, and we need to sort of do a spectrum of that as well.
So somebody is asking from Tariq Abdullah from India, what is the smallest size of plant which is commercially suitable for the Haisana implementation of Haisana technology?
I don't know what would be economically the minimum. It's as with any steelmaking process, the bigger, the more economically interesting. A small plant has a large of disadvantages on energy efficiency compared to a large plant. And I think it all depends on your local conditions and the raw material mix you can use, and whether you can, for example, have a good income of a side stream like zinc. What scale is really, but I would imagine that anything under 500,000 ton would struggle to be economically feasible.
Right, sir. And sir, due to the usage of coal and iron ore fines, there is a chance that more amount of dust is coming out. So what is the flue dust coming out of the gas? What is the composition of this flue dust? Mr. Venkatesan J from India is asking, what is the composition of the flue dust that is coming out?
Yeah, so we've measured the dust, and the dust is largely iron oxide actually, but anything that goes in there that is volatile at the temperatures of iron making, so whether it be zinc or lead and that sort of stuff, will all be part of that dust in the end. It will end up in the dust. But the dust is very much iron oxide, and what we are trying to achieve with the zinc recovery is actually that dust is largely zinc oxide, and it's a deliberate target in that case. The actual dust losses are not as great as one would imagine. In the original off-gas duct, because I said we replaced the complete off-gas duct. In the original off-gas duct, we had a lot of dust losses, but by redesigning the off-gas duct and having a section in there that actually is very efficient at capturing dust, remelting it and letting it flow back into the process, we see that the dust losses have decreased dramatically, and our modeling for an industrial scale plant shows that if you scale that up, it will improve even further.
Right. So we come to the final question now that the industrial facility will be starting from the next campaign. Could you give us a timeline about the commercial availability of the technology?
Cool. Now, I think that the first industrial scale Haisana and demonstration plant will be operational somewhere in the middle of the 2020s, so 2024 to 2025-ish. And I think after that, depending on how successful it can go quite fast by having one or two more industrial scale Haisanas. And I think at that time, commercialization will also happen. So I would say commercialization, real commercialization, second half of the 2020s.
So with that, we come to an end of the question and answer session. If you have missed anything here, I would request you to kindly, shed light on anything we have missed or something you would like to add.
No, I think it was a good discussion, and I think most of the things that I think I would want to say have been covered either in the presentation or in the questions.
Thank you very much, sir. From all of us in the Steelman family, thanks a lot on sharing your insights on this emerging technology. Thank you very much. And thank you very much, participants, also for joining in. And do keep a lookout for new webinars on this space. Thank you, sir. Thank you.